All right, welcome everybody to the first of hopefully many How It Works screencasts that I'll be doing. This time I'm going to be doing it on something new for 4.0 that I feel has really changed how CanJS is written. It's a pattern. It solves a pattern that I didn't really realize that I had been doing over and over and over and over and over again. And then it really drastically simplified it. And this is something called CanKeyTree. And what CanKeyTree is it's really just useful to making tree-like structures. That I think the real special thing about it is that it prunes the branches nicely. If like kind of one node becomes empty, it will just recursively prune those nodes upward. And because it's integrated with CanReflect, it has all this nice setup and tear down kind of functionality you can weave into it that make it solve patterns like adding event delegation rather easy. In CanJS, it's how we use it for registering all event handlers as one of the common uses. So with that, I'm really just going to walk through the documentation and then a little bit of the source code and try to keep this to like 15 minutes. So CanKeyTree, you initialize it with the structure of your tree. And this means I have a tree that's only going to be kind of, you can think of it as like 3 nodes deep. There is a root node that's going to be an object. It is going to have children that are arrays, and then the arrays can have values inside them that are what we call the kind of the leaf values of the tree. Once I've created a tree, I can add items to it, given a kind of a path, and the last value you could think of as the leaf value. And in this case, because I have an object and an array as my structure, the outermost, what the key tree is going to contain after adding Illinois and Chicago will be an object with an Illinois property that points to an array that contains Chicago. And if I kept calling this, I would get multiple Chicagos would keep being added. So let's look at a little bit more of an example. So there's also callbacks that you can pass to KeyTree when you want to listen when the first item is added or when the tree has been removed. That's really useful for knowing when setup and teardown logic should happen on something like a define map. But let's just see more about that general structure. Let's say I create a key tree here that I really want to use for registering event handlers by maybe I wanted to set up my own event delegation like system. So if I had different handlers, and I wanted to register them within the tree structure, let's say I wanted to listen to handler 1 on click of an LI, and handler 2 on click of an LI, and handler 3 on click of a span. This would create a structure that looks like this, right? It would have a click, and then because it's object, those objects underneath, it would have an LI, and then it would have an array of the handlers inserted in that tree structure there. Now, anybody might be asking, why do you use tree structures instead of just a list? Of course, I could just, another way that I've seen jQuery kind of does it this way, they just have a flat list of handlers, and then the handlers are all decorated with meta information, which event that they're listening to, and which CSS selector. Well, trees are fast, right? If I want to get all of the event handlers very quickly for clicking of an LI, I don't have to loop through some big list. I can just single order one operation read down to my handlers for clicking of an LI. So this is a big reason why trees are really nice for performance. So when the key tree builds this type of structure, you can access it using get. And you can say, hey, get me all of the handlers at this path in the tree. So this would give you the 2 handlers for the LI. What's nice about this is you can also get all handlers for one branch of the tree. So I can call, hey, give me all click event handlers. And that would recursively go down all of the children and grab all of the handlers. Delete can be used to remove items or entire branches from the tree. So I could remove the clicking of the LI, or handler 1, click LI this handler, and then the LI handler would look like this. I could delete all of the click handlers, and then the tree structure would be empty. Now, one thing I could do, and then I talked about it, but I don't really show it here, which is if I removed, after I removed this click LI handler, if I removed this one, this property would automatically be deleted. And then if I removed the span, not only would the span property be deleted, the click handler would be deleted as well. It kind of will make sure, it'll prune all parents that are empty, essentially. So the advanced use of this, you can do cool things because it uses can reflect. So if I wanted to make a event delegator library, where I could add the context for what I want to listen to, what event I want to listen to, the CSS selector, and any handlers, and I could remove handlers like this from my event tree. I can do that with this following delegator, and I'll just kind of show how it works real quick. One thing is that you can create custom types. So I'm going to show this at the bottom. Is I've got this what I want to do. My key tree structure is going to be a map of elements. So the root is going to basically contain keys as elements that point to a delegator instance. And delegator instance sets up the binding and things like that for various CSS selectors. And then the CSS selectors point to an array of event handlers. So you can think of it as like there's an event, there's an element key that gives you your delegator. There's a then there's a wait, let me see, how did I do this again? Oh, then there's a event key that points to your object. Then there's your CSS selector that points to your handlers. So really the magic for this is all in the delegator. Everything else is probably pretty plain. I'm going to create a delegator that when a new node is created in this tree, in this case a delegator node, if it's not some basic CanJS type, it's always past the parent key. In this case, the parent key is the actual element that we want to delegate on. And then I'm going to contain all of the events that, these are really the keys from Delegator, the events that we want to listen to. And here's some, we basically need another container for all the event handlers we've listened to so we can remove them later. And I'm going to implement canReflects methods so that it can key tree knows how to like add keys to this delegator type and remove keys. Again, keys are going to be the event names. So it's like on this delegator, someone's now binding on click span or something. Or they want to delete all of the span event handler or the click event handlers. This is handlers by selector. That is the next object down. That would be like an object that has you know, your span or your LI that you want to listen to. So essentially all I do is I'm going to keep which handler I'm about to bind so I can unbind it later. And I'm going to, on my element, add my event listener to call this handler. And then I just go through my handlers by selector, basically my child. I know my child element, my child object that is that map of selectors to their handlers. And for each selector, basically what I do is for each selector, I'm going through the element from the target the event happened to all the way up to the parent. This is how you implement event delegation, by the way. If you've never done it, go all the way up to the parent, see if any one of those elements matches the selector. If it does, I'm just going to go through and call all the handlers for it. So, oh, and I keep my structure. So I need to know like what's the next, you know, my children. I keep that in events. So if someone wants kind of your child handlers by selector, that's what they would get the key. right? So they'd say, get me the click and give me the structure underneath click. Well, that's why I keep that in events. And then for delete, I will remove the event listener and delete the events. The nice thing here is delete is only called when all of your handlers have been removed, or someone tried to delete that branch. So like I don't really need to do any kind of handler cleanup or anything like that. I just remove my event listener and kind of delete those associated data that I've stored in my type. And then get own enumerable keys is to let it know like how big, how many children this has. Size will be used. Like it's basically measuring the size. So if you implement get own enumerable keys, it tells it how many child nodes you have. So with that, that's all you have to do. I mean, this freaking blows my mind. I can't tell you, having been one of the core contributors to jQuery's event delegation system, how much easier can event tree makes doing stuff like that. So it's really nice, and it gives you all this power. So if you just want to delete, hey, every single event handler, a delegated event handler on the body, well, you just do this, and the system, the key tree just takes care of it for you. Okay, so let's see how it works. It's actually pretty simple. So I'm going to start going forward. I think it's a good practice. I'm going to add use cases for everything, then a simple use, and then at the bottom, how it works, with hopefully links to .code docs for it. Okay, so let's just go through this high level real quick. It's actually fairly simple when you understand can reflect. So this only depends on can reflect. So it has that level of abstractness. It doesn't really need to know about its type as long as the type implements what can reflect needs. I have a helper to know whether a particular type is one of the built-in types of JavaScript, like maps, date constructor, things like that. I want to treat those slightly differently than user-generated types, so I have this way of checking that. If basically, if it's not, doesn't inherit from object, if it's not inherit directly from object, if it's not the object prototype, and if it's if you call the object prototype toString, if it returns object then something, it's a built-in type in JavaScript, unless someone's really mucking around with their environment, which I'm assuming they don't. GetDeep size. This simply is going to recursively walk down the children and call deep size again to essentially get how many child nodes there are. There's a level which we can use to like know how deep we are. We don't really. I'll show that's used somewhere else, but for the most part, you can see what it's doing is it's going to loop through each item, and then for each value, for each kind of key in the value, it's going to say, hey, give me the size of that, and then count. And it makes sure that it's not going to go too deep in case you have things that also could be looped through. You know, not everything ends in primitive, so that's why there's this level to essentially count to 0. This will be used later. These are the helpers, essentially. GetDeep. This is going to basically go get all of your handlers. Same kind of thing. It's just recursively going to go through each key in a node and then call deep on it, and it adds everything it finds at the end to items. So canReflect here has this add values, which if it's an array, just will add what's ever here to what's ever here, like kind of push it in, mutate it. You'll notice we expect right now all of the final structure needs to be array-like. So the final kind of container in your tree structure needs to be a list-like, could be an array or a set or something like that. It's not like a map. It's not a key-driven thing. So there's just some type checking to make sure that it's actually like that and throws a warning. Eventually, I do want to support that other if you have maps in at the end, but there's no reason to do that for CanJS, so I didn't do it. ClearDeep, this is what recursively just goes and removes all values. again, just goes through every item, calls clear on it, and then deletes the key that was pointing to that node. So essentially, we keep the parent, and we clear out the child, and then delete from the parent to the child that key. Okay. So now we've got some simple helpers to walk through that structure. Key tree. All it does is it stores the callbacks and then the tree structure, which is like that array, of your types. And then depending on if you can actually for key tree, you could actually pass it something that is not. You could pass it an instance as your first item instead of a type. If you did that, it'll just use that as its root of the tree structure. Otherwise, it's gonna, if you passed a type as the first argument or the first object in this tree structure, it will create that new type and use that as the root. Okay. So delete is the most complex function. Everything else is pretty straightforward here, I think. For add, essentially what we're going to do is walk down to everything but the last key, and we're going to build up. If we don't find, so we're going to start with essentially the root place, like our placeholder where we're starting, and we're going to say, hey, go get us that key. If that key doesn't exist, then, and by the way, I probably should be just checking if it's undefined here. That's actually faster than this not check, but anywho, if we're just going to look, if there wasn't a child node, we're going to get the constructor at that point, and we're going to create a new instance of it. We're going to do it in one of two ways, depending on if it's a built-in type or not. And then on our parent, we're going to set that key to the new child node instance we created. And we're just going to we'll just keep on building the nodes of this branch that we're building up until the second to last, up until basically the last key. And then what it does when it's at the last key is it just calls this can reflect add values, which if it's an array is the kind of last node, it just will push onto the array. And then we call on first if our root was empty at the start. That's pretty simple. Get node is ridiculously simple. We're just going to do that same kind of walking of keys to find our node. And if we don't find it, just return undefined. Get is a little bit more complex. It's going to go get that node by walking through the keys. It's going to, if you were asking for did it get halfway through the tree structure, not all the way deep, then what it's going to do is it's going to use that GetDeep to recurse and say, hey, go get me from this node, go fill up this items, which we always use the array type at the end of our structure. We always create an instance of that so that you could have sets coming back if that's what your container for your handlers or whatever was. Go fill those up. Basically keep recursing down this child to go get and put all items in here. Delete. Now this is the one that's a little somewhat the most is probably the most complex, and we saved the best for last. The real complexity for delete is the pruning. Essentially, we have to keep our path to whatever part of the tree that was deleted, so that when we go delete that key or that part of the tree that we want to delete, we can kind of back up and keep walking kind of backwards up the tree and checking if our nodes are empty and then pruning them. That's essentially what it does. So here's the path, and what we're going to do is go to the second to last key, and we essentially just, as we find nodes, as we kind of walk down nodes, we're just going to put those into our path. And at the end of this, we're going to have our path, and we're going to have kind of which is the parent node of the last key that we want to delete. So I'm going to go through to the more complex branch. These branches are well, if you just try to clear the whole tree, just clear the whole tree. If you if you were trying to delete something at the very end, well, then we're going to call can reflect remove values on that array to remove that value. And then otherwise, if you're trying to delete like a whole branch from a tree, what we're going to do is make sure you have we get the node to remove, and then we need to clear everything on it, all of its children. We're going to go clear all of those, and then delete the parent's reference to all of its children. So we've done that. And then what we have are paths, and we've got to kind of like back up the paths essentially to prune everything. So what we do is, hey, our parent node, which is like the node of our child we just deleted, is that empty? If it is, well, go up to the parent. The new parent node is the previous one in the path, because we're iterating backwards here. Delete it. And then again, we'll have a new parent node. If that's 0, delete from its parent to its child, and we just keep going and deleting this way. And then on empty, we're done. If our root is empty, we call on empty because our tree is now empty, and that's it. And size is just, we already saw how to do size. So that is CanKey tree, probably one of the most useful little low-level utilities I've created. It's got a lot of potential uses for, I think, kind of open sourcey programming. Hopefully people check it out and use it for other things that I haven't dreamed up yet.
So can you think of any of those uses? Like event handlers seems really obvious. That seems like what it was built for. Great. I'm trying to think, like, where else do you need this? It's like a static data structure that like is this, it's exactly what you set it ahead of time, and then you want to like pull and delete things, and the trimming is the big thing, right? And the ability to like you said, make that Delegator custom object.
Yeah. So
and then I guess there's the callbacks too, which is pretty nice.
Yeah, it's a lot of times in jQuery, right? jQuery's data could have been done with this. Its event delegation library could have been done with this. jQuery's event system could have been done with this. Anything where you have kind of that one-to-many callback relationship is where this thing is going to be really good, especially where when certain nodes of the tree need to like do stuff, right? And you only want to do it once, and when that branch gets deleted, you want to like only tear it down once. This is really useful for that. So yeah, I mean, and all those things are kind of, well, except for the DOM data, they're places where there's event handlers. But DOM data is just like, is a kind of a tree structure that's based on elements that could use this as well.
Now I'm assuming, and I think I know the answer already because of all the size uses, but you couldn't use like a weak map with this and have a self-cleaning one. You'd have to like manually delete things when you're done with them to have this actually work.
Yeah, there's no, because weak maps don't have a size, right? And they're supposed to kind of clean themselves up, right? I think it would be fun to, I've wanted to make this, because I like the API. API is really nice, is I wanted to be able to make it so that it can still have weak maps, but it can only prune up to the weak map. And then it's like, I don't know what to do anymore.
Right, yeah. That would be cool.
Yeah, which would still be really useful. You would just never be able to tear down the weak map. And that's actually why I put the weak map, that's why in the API, I left space where the root can be an instance of something, because I think it's going to be very common where you'd want the root to be a weak map and then everything underneath it to be, normal tree structure.
Because that might be how you do, like you said, the jQuery data thing could be like the DOM node is the root element thing, so it needs to be a weak map, and then the stuff inside it is.
Yeah.
Yeah, exactly.
Yeah.
Looks really cool. I like it.
Yeah, and then hopefully tomorrow we will see how CanEventQueue or CanQueues uses, when you have the new queuing system plus this trees, it makes kind of managing your own event handlers and things like that, and then running them in the right order much easier. So stay tuned for that for tomorrow.
So this is like the new hammer of Thor, which every nail will now be using CanKey tree.
Yeah, well,
Love it.
definitely all of CanJS's event handling is all using this now. And the nice thing is, like I said, especially that pruning and the ability to say, like, I just want to delete this partial branch. That was stuff that was kind of like implemented here and there in CanJS 3.0, like kind of on an ad hoc basis. Like can define, like you could do it, but you couldn't do it on like can computes. Actually, I think it was the opposite is true, where you could just say like, I want to remove all event handlers, just call off and just blow everything away, right? We kind of added that ad hoc into things, and now because of how easy, because those were two different things, right? One is a key-based event system, the other was just like a single value changing. So they had like differently separately architect built handler systems because their structure is very different. But now there is no, like you can have wide variance of structure, but it's all managed by can key tree. So it's much better.
Cool.
Well, thanks guys for joining, and hopefully see you tomorrow for Qs.
Excellent.
All right, later.
Much later.